Okay, so hello, my name is Kush. Today I'm going to be talking about the evolution of search, which is going to be a history talk about the developments over the last several millennia, centuries, decades, leading to now, and perhaps where we're headed, or speculation of that. What you're seeing here is a automatic speech recognition system that I've been building for the last long while, and I keep iterating on it. And I thought this would be this is the first time I'm using it in public. So hopefully it works. It's probably gonna hallucinate a lot and whatever. But I'm trying to use the best model I can, and so this should allow you to understand me when I'm not legible myself as speaking. Also, if you get lost, you can track that there. It'll perhaps automatically highlight certain phrases and names and so on that I know I want to hit. Moving on for that. A little bit about me. So I'm a freelancer. I most often build and design software for clients, web apps, games, mobile. Over the years, I've been involved in a lot of VR, sort of real-time stuff. I have a real passion for real-time engines and sort of things, as you can see here, low latency stuff. Most often, though, I sort of build stuff for myself, and then I fund survival through working for other people in the sort of capacity of freelance contracting. My background actually is not in sort of any of this, like data science, machine learning, software, or any of this. My background is film and animation, and also like industrial design. But I just love art and technology, so I sort of love remixing them. And so what you're hearing in this talk, which is a history of perhaps information retrieval, is not necessarily coming from a place of something that I was taught, so it may contain errors perhaps, but mostly it's just because I'm curious about a subject. I dive deep, and I really love learning history, so I figured I'd deliver a history lesson based on what I know. So before I do get started on the talk itself, I wanted to sort of get a sense of the audience makeup. So perhaps can I get a sense of how many of you are software engineers? All right, so around maybe 10%. What about designers? I doubt any, maybe few. All right, I see it. I see a couple. What about business people? I don't know. It probably sounds like a dumb thing to say, business people, but that's how illiterate I am about that. What other sort of job titles or domains that I have not mentioned you might be in? Just say them out loud.
Data.
What's that?
Data.
Yes. How many of you are data scientists? Okay, data engineers, if that's a different thing, if that's a different thing the guy says. So brilliant. That gives me a sense of the kind of vocabulary I might get away with, and the kind of stuff that I might explain, as well as the holes that perhaps you'll be able to fill later on. As you can see, the system has completely gone awry, but I have a way to make up for this. I'm gonna just right here reset, and it's just gonna sort of start off from here on out. Fine. Yes? No? Are you gonna do it? Live demos. Come on, are you gonna work? You can do it. You can do it.
Do you need to adjust the code?
I honestly, I would be down to do it, but I don't believe that I. Come on, hold on. Okay. This is an attempt to have it work again. Perfect. It's working again. Okay. So So let's get into it. I wanted to start by addressing, so the way that I've structured this talk is like a series of questions, basically challenges that arose over the course of the last millennia and centuries, and how we address them. So the first thing I wanted to do is ask ourselves, what problem are we solving really? Which is the problem of finding information, the right information at the right time. So it's not just finding the right thing, but also at the right time, and that's really the challenge that has led us to have all these innovations over the course of the last a long while. If you can imagine standing in a room of, let's say, unmarked boxes, and you have to find information that's contained in one of the boxes. One strategy you could use is go through all of the boxes one by one, and eventually you will hit what it is you're looking for. But that would be too time taking, and perhaps it would not be the right time by the time you do find the information. So the factor of right information might be there because you have actually in one of the boxes for sure the piece of information you're looking for, but to get to it in a more optimal fashion is something that you perhaps can build for, design for, and so on. So that's kind of the field direction of information retrieval is over the course of the last long while, people are trying to find ways to scale, retrieval. All right, whatever. So, in the interest of starting the story as far back as possible, because I love going as far back as possible, we're going to start before the written word even. Around the Roman and Greek Empire or times. So back then, one popular technique that people used to use was the method of loci, which is a memory palace for information retrieval, recall. Because before we had the written word, you still needed to, memorize stuff or recall facts that might be important. For example, when you're giving a speech. So an auditor might use a memory palace as a way to associate information spatially to a location that they may already be familiar with. And then while they're giving a speech, that includes various facts or various pieces of information that are disparate, they can just walk through that room and say that was about that chair was about that one, and so on. So this was a technique that people used to use to be able to store information that is not necessarily obvious, that like your family's names or your friends or events that happened in your own personal life in the last while. So that would address the problem of what did I stash in my head. That's the initial solution to that. But as people went ahead and took on bigger projects and also faced the challenge of transferring information to multiple people, as well as retaining information over the course of multiple lifetimes, this memory palace did not scale. In fact, the memory palaces were so sophisticated, so complex and so dense, especially for speeches, they wouldn't even last beyond an evening. Like people would really rehearse them before a given speech, and then they would kind of drop them after the fact, because it's kind of just a tool built for that specific purpose. I don't have a memory palace for this one, so I'm going to forget a lot of stuff. So that's why I have like some notes here. But I also don't need the memory palace now because I'm lazy. So once people realized that knowledge needed a body outside the brain, that retrieval changed as a problem from being just recall, our own brains, to something else externally. So we turned to writing. Effectively externalizing the data into a written form solved the problem of not having to memorize everything, but then the problem becomes, how do we keep track once it's written down? Like this is a challenge that scales for the last forever as information grows, as the need for information and the speed at which you need it grows as well. So even as far back as 700 BC in the Library of Alexandria, we had people, librarians, adding colophons, which were these sort of sections to tablets that would contain the author, the subject, a little bit of aboutness of what that information was written in that tablet, and that little bit in a corner would help you recognize faster than having to read the entire tablet what it was about. This little bit of aboutness was metadata, the earliest metadata, like 700 BC, right? And that's exactly what we have now. So we can trace a line from that to concepts that we use every day. I don't know if they call them metadata, whatever the Greek or Latin word for that is. But that same thing you see also in 300 BC in the Library of Alexandria, when you have like hundreds of thousands of scrolls. You have these tags that would be attached to them containing information about what that scroll is. But now that you have hundreds of thousands of scrolls, that seems also quite inefficient and impossible to walk through the entire library, look at every scroll, and find a piece of information about how to architect a house for a given client that you might have. And so this librarian, Callimachus, that was working there, or he was leading it in 300 BC, came up with or built a project called the Pinax, which was a index. This was the first example of an index, which was information about the scrolls outside of the scrolls themselves. So this was a separate shelf of scrolls, or shelves in fact of scrolls, that documented a map of where all the other scrolls were. So this was an actual index outside of the index, or outside of the documents themselves. And in that sort of index, he would have authors, titles, subjects, as well as first lines or summaries of the document, which is like very kind of similar, you can see, to some of the ways in which we browse data right now in user interfaces. And so even as far back as that, these ideas were already being put into daily use, and in an institution as big as the Library of Alexandria. Similar efforts were, of course, being taken in China for bibliography and classification, in the Arabic-speaking world, in so many different places, in parallel or over the course of 100-year difference or so on. But I'll skip to the next era so that I don't dwell on this forever. Very important and worth mentioning is that the story that I'm telling is, of course, made up of the pieces that I could put together or that I cared to put together in this timeline, but that does not represent what the story of information retrieval actually is, or what the various people over the course of humanity contributed to it. Because I feel like it's very important to recognize that the history is always kind of told by the point of view of the victor, and there are so many people that contributed to, or tried to contribute to, or build solutions that we will never hear of because they weren't documented, or they were not the ones in the leading sort of direction of the world, or the ones writing the history books. The next big challenge that we faced was with the birth of the printing press. Knowledge explosion, a lot more people are reading, a lot more people are seeking information, 16th century, so we're jumping quite a big time scale. And the question that arose was, how do we even know what's out there? So people started exploring the idea of universal biography. And so this guy, Konrad Gessner from, I will pause and fix this. Alrighty, is this going to work? Yes, it is. So this guy, Konrad Gessner, created this project called the Bibliotheca Universalis, which was a book that he published that was a catalog of thousands of authors from around the world and their works, but it was a global one. So this is the first of its kind, a global index curated by this guy that was being published and distributed around the world. So finally, there was a way in which, let's say, a librarian, a scholar, anyone in a given part of the world could at the very least know what's out there in a different part of the world, and then they could seek that information out by perhaps purchasing that work or going to a library in a given city that might actually have it. Maybe that information was in this catalog as well. But at the very least, there's no Google back then. Also, Google sucks, but there's no search engine back then in that sense. So this provides a good directory of information that exists. So alongside that, he's cataloged this information as a list of authors and their works. But people really start to ask questions around what does it mean to organize information? How should we organize information? Francis Bacon in 1605 contributes to this by saying we should perhaps have a conceptual organization of knowledge. He comes up with these three categories: memory, reason, and imagination, under which he says we can simply walk down the sub-paths with each category and be able to sort all information that exists in the world. So at the very least, people are trying to think of, like, if we are going to do this job of cataloging the entire world's knowledge, there must be an optimal or really like an elegant way, very software engineering kind of thinking, like let's come up with an abstraction. And so similar works are happening or being undertaken by a lot of different people. In the 1800s, Dewey Decimal System by Melville Dewey is created as a way to standardize also not just like knowledge abstraction around like concepts, but also a system that could be then used across locations, across the physical world, where a knowledge seeker could walk into a library in one city and understand that within the 500s you'll find books on one category, in the 900s you might find history or whatever. And so this was like a universal system that now you had. If you could just understand that system well enough, you would simply be able to much faster get to the knowledge that you were looking for, because it was getting adopted across the board. Vancouver Public Library, I'm pretty sure, uses that as well. Yes?
Sorry, I just got a little point. So it also seems like people's awareness of how much knowledge is out there kind of grows over time. And this is dating myself, but I went to Microsoft's first tech ad, and they had a nice purple bag with some things in it. One of the things they had was a book that had all the web pages in the world.
Mm-hmm. All of them.
All of them. Literally, they did.
Sounds hard to believe. Yeah.
Within a couple weeks.
Mm-hmm.
But I'm not sure if they've kept it up or not.
I mean, it's interesting you mentioned that because you brought it up. Perhaps I'll mention. So I was recently at the Internet Archive event at the the Permanent Library, that building, very cool building, and they they're sort of trying to build another project. I forget which country it was, but a sort of public project around cataloging all domains that exist within that country. It may have been Netherlands. I forget right now. It was in the Netherlands, yeah, and so you could simply go there and like kind of look at a bird's eye view without sorting, without organization, just sort of thumbnails that of all websites, and you can sort of zoom in and then of course visit the website itself, and of course Archive themselves have various other initiatives like this, and people around the world. Yeah, I mean, I think fundamentally, like, it is such a enticing idea, the idea that you could truly know what exists in the world. Like I mean, we are kind of not spoiled, because I have cynical sort of view of it, but we have a map of the entire world, like actual map that we can on a street level view. My problem is that it's not a public map and it's owned by a private company. That's insane. But beyond that, we do have a actual map of the world that we can actually figure out which street in Thailand or which street in India or China or here immediately as we feel. So. But yeah, I think thanks for the question. So with the Dewey system, we had this sort of ability to access information from like a point of view of someone who was not necessarily part of the librarian class of people. If you could just understand the system, you had a little bit more access to knowledge because now you could navigate your way around it. This idea was, I'm going to get back into the idea a little bit later as well, I believe. Is efforts towards that goal. But as we started indexing information globally, like I said, we asked the question, could we index everything humanity has written? And so there was, beyond the effort to organize knowledge in a rigid structure, which is like categories, topics, and so on, the Charles Cutter created a system called subject headings, which was a way to approach knowledge from various aspects or various facets. So this was, let's say, if you want to learn about trains, you should have like tags or sort of these subject headings associated with various different pieces of information, books, cards, whatever else. And so you could simply go and look for that box of cards about that, and you'd be able to say, okay, these are all the books that are relevant to this. Almost like I don't know what the term for, maybe glossary or something else. Similar, or it would find you like books about railroads as well as it might find you books about some other category that does not belong in a 600, 700, 500 kind of simple classification. The Library of Congress famously put the Charles Cutter system into use, and what they also did was started distributing. Printing and distributing these card catalogs around the world, which is a major move because now you basically started having a system of indexing information in one place and then sharing it with everyone. So you kind of start building a shared index, a distributed index. Not quite a distributed because, it is still happening from concentrations of power, but a distributed system, the nature of it changes as we get more and more democratic into the world. But this was a big move because now you had the ability to index a lot deeper, more intuitive subject headings and so on, because it was like one guy in one room was doing something and another person in another country was focusing on this subject, and so you really had a rich index coming together. Another individual, S.R. Ranganathan from India, in the 30s was talking about principles around knowledge indexing and retrieval. And so he was trying to come up with, he came up with these 5 principles. One that I really loved was save the time of the reader. And basically the idea is that you, instead of organizing information for the librarian to find for the reader as they approach them, it should perhaps be organized for the reader themselves, and they can simply approach the subject from various facets, like time period, place, topic, again with the Charles Cutter system, and be able to find it. This, the way that he wrote about it, and if you look into the work, it's, you can draw a straight line from that to interfaces nowadays for, like, when you're doing e-commerce and so on, for brand, price, category, I mean, whatever it may be. These are direct descendants of that idea of, instead of having to say, I have to go to, let's say, DJI's website and go to the mic section and then find what they've told me, we can simply say, I'm looking for a small interface, I'm looking for this bandwidth, I'm looking for this and that, and be able to find exactly what you're looking for. So those those facets are a direct descendant of what Ranganathan was talking about. So another really, like, quite forward-facing project that was being undertaken at the time. Actually, I've completely missed one thing, which is, I, by the way, made these sort of little visuals. They're all kind of interactive, and also they're 3D. So these are all, they're all coded up. Yeah, 3D. Yeah. Put on your glasses. So and it's like these scrolls, whatever. What am I doing? I totally missed these. In any case, and these are like little books. You can just hover over them. And just having a lot of fun. Completely irrelevant to all of this. But moving to the next thing, this project called the last visual actually, this project called the Mundaneum by these guys Paul Otlet and Henry Lafontaine in Belgium, and their goal was to create a card catalog of all the world's published knowledge. But what they did was also, like, they had this building or whatever of like lots and lots of these cases of drawers in which they had card catalogs for all kinds of knowledge, and they had built a service where they started in 1895, and by like 1930, I think they had like tens of millions of cards, and you could basically write a question on a piece of paper, properly, whatever you want, ship it to them in Belgium, and they would go to the various drawers, figure out what information answers your query, put together an answer, write it down, and they would mail it back to you. So this was the original. This is like a paper-based search engine in the 1930s, like a direct precursor to the current knowledge retrieval interface that we are all familiar with. I thought this was cool as fuck. Like, that's crazy. Like they were actually doing exactly. They were trying to do what we now take for granted without having the sort of internet technology and so on. So internet technology. Anyway, you get it. So yeah, that's like. I thought just was like incredible. But also, like, what I want to highlight there is a core theme in my talk is that everything has been done before, and that people have been thinking about these problems for a long time. Somewhat anti-hype, if you will. Like I love being in hype cycles because everyone's contributing sort of more, and people are just being afforded more opportunities to have meetups about this and like just get together and talk. But what I dislike about it is all the just scam shit, like Silicon Valley, like just billion, trillion, quadrillion, exchange of money. But if you look past that, you realize that so much, for example, right now, what we take as artificial intelligence and ML and so on was figured out 50 years ago, 70 years ago, and I'll get into that in the rest of the talk. But also just core ideas, because we have wanted to do this. We have wanted to have a futuristic view of the world for a long time. For them, it was futuristic. They made it happen in the capacity that they could. Think steampunk, think whatever. And we perhaps should and are trying to do the same now. But to sort of forget history and just imagine that what we know now is like sort of a shadow of what we used to, and not learn about it, I think just does a disservice to our future projects, current projects, etc. Probably it's obvious, but I just felt like I needed to say it. Skipping past to the advent of digital computers, let's say mid 50s, I guess. this guy Hans-Peter Loon at IBM asked the question, can statistics stand in for understanding? And so this is him treating data, text especially, as not sacred that needs to be read and understood, and the meaning needs to be like go through the human mind and actually perceived, but rather simply as words that are like data signal that can be processed as numbers and counted and sorted, and sort of treating it very industrial, mechanistic style, as opposed to, again, the general perception of language before that, which has a few different outcomes. In 1958, he created this system for generating automatic abstracts. So an abstract out of a given document or a piece of information, which would allow you to, which was done through counting frequent words and finding what are relevant sentences worthwhile enough to extract into the abstract. And the system that he built was called Keyword in Context, Quick. And you can sort of see that the way that he organized the abstract system is very, you can draw a straight line from that to Google's 10 blue links. And when you see like a little abstract on the page showing you what the page might be about, that is very much automatic abstract generation. And so just to have a quick little glance of what you might be. So you can imagine a system like this being used from then on forward to have just speed up the ability to index in a mechanical fashion, as well as perceive the relevance of a given document once you have the results back based on the abstracts. Now that we're doing now that we're counting and processing data as non-sacred based on statistics, people also start to ask, could relevance be quantified automatically? So relevance of the results that have appeared after a given query to the query that we had in mind, because that seems like a very subjective thing. Like, okay, I found some documents. Is it relevant to my query? And perhaps there isn't really quite a solution to this. Even now, we all know, like, we have systems currently in production, AI everywhere, where answers may come back and there is still quite an issue with if it is the best appropriate answer for the query that I had asked. But people have been thinking about it for a long time, and so I'll build on the topic of how they approach this problem. There's like so much to say about like Claude Shannon and information theory and like just infinite depth there. I was telling Gordon earlier, not gonna get into just about anything. Plus, I'm illiterate, so I probably don't know anything about any of this. I just like gathered whatever little bits that I care about in the little bits that I build. But someone really worth mentioning in this space, a massive contribution that he made was Cyril Cleverton, who was at Cranfield at the College of Aeronautics, and he created these Cranfield experiments, which were basically a scientific approach to figuring out if documents are relevant to the query that retrieved them. And so, what happened just now? What the fuck? Okay, that is the first time that happened. Is this working? Yes, it is. Thank you very much. Alrighty, so this basically was a system of evaluating again. What he did was this: he manually at the College of Aeronautics went to experts in the subject domain and gathered various queries. He then had a set of documents, and he asked them to rank, or basically which ones are relevant to the documents, relevant to the query, as well as which are not. And so now he had an actual ground truth data set, supposedly or seemingly for the first time in this field of information retrieval, where you could actually say, for this given data set, for this given set of queries, we know which ones are relevant documents and which ones are irrelevant based on information we've collected from an actual source of experts, or a group of experts. And so that became significant because he is the one who introduced the concepts of precision and recall, which some of you may be familiar with. And precision is basically what fraction of retrieved items are relevant, and recall is what fraction of relevant items are retrieved. If that sounds like a tongue twister, what it really means is one is checking for how relevant they are, the things that have been already retrieved for this query, or the other is like, did you actually retrieve the stuff that I wanted, or did you miss some? So you oftentimes there's systems compromise between one or the other, or there's like a sort of balance that you strike based on the user experience that you're creating. Let me think where I want to go next. So this was massive because now you had this data set that he had published around the world, and people could start comparing approaches. So if you had one approach to index data and retrieve information, you could globally from a different continent or whatever say, this is my approach, and on that given data set it works this well. Kind of benchmark maxing is now possible, and so you can basically start having labs competing and releasing their kind of the way that stuff is happening now, but hopefully more intellectually rigorous. So moving forward, next question we ask is, how do we tell signal from noise? Because if we're treating this data as signal, just purely to be counted and worked with, how do we differentiate? So did I miss something? Just one second. I don't believe so. I will skip Marin and Kuhn's. I know, horrible thing to do. And I'll move directly to the vector space model. So basically, if you've heard of vector embeddings, I'm pretty sure everyone has here. Currently, they're used as like a core ingredient of the transformer architecture, embeddings in general for query and retrieval, various different, just like ML approaches use them. The idea of vector embeddings, or vectors being used for data processing, originated or was at the very least popularized by Gerard Salton at Cornell in the 1950s, and in the system that he was building called SMART. You can think of it as like vectors are, actually you guys are probably already familiar with it, but still, if you're not, vectors you can think of as like a list of numbers. So a single vector is a list of numbers, and in the case of the experiments that they were doing at the time, it would be the count of words in a given document. So let's say I have a vocabulary of words from A to Z, apple, banana, zebra, whatever it may be, and you have the counts of how often the word appears in a given document. So in document 1, 0, 0, 0, 0, 0, 5, 1, 0. So that might be the count, and that represents the single vector. So you have the vector for a given document, and then you might have a vector for 10 more, and then you might have a vector for the query that I'm asking. My query might be, how high can this given airplane fly? And so you can have the counts of those words as well in that query. And now you compare those two vectors. The way that they were comparing it back then, and is the way that we compare it now still most often, is cosine similarity, which is basically a way to calculate whether two vectors, which again you can think of them as lists of numbers, or you can think of them as coordinates in space. So if you only imagine a 2D vector, you can easily imagine like that's just like that far and over there, so that's 2D. Or a 3D is like that, there, and there. But just imagine 4 dimensions or 5 dimensions. If you cannot imagine, take it for granted that computers can process that. In that sense, the cosine similarity measure allows you to tell whether two vectors are pointed in the same direction or similar direction, or whether they are much farther opposite to them. And this allows you, just purely on like a very sort of data processing way, to tell whether two documents or two word count lists are separate enough or similar enough. Surprisingly, it worked well enough for it to be useful back then. And I would posit that we have basically been using the exact same paradigm, just coming up with new ways to generate those vectors and to work with them. So now we're using neural approaches to generate those vectors, while then they were using counts for vectors. Blah, blah, blah. I'm just going to confirm that this system is working or not. I know, I don't know why I love doing like always challenging myself with techie stuff, but if you're not going to challenge yourself, then it's boring as fuck, So, all right, come on, man. Don't let me down. You're embarrassing me. Is this working? One more try. It might be that my GPU at home, which is what I'm using for this, is like just like yelling right now, like like the fan's just going off. So it might just be a matter of me waiting for it, but I don't think I'm going to wait anymore. So I'll keep going. I already discussed how the vector space model kind of works. So in as Gerard Salton is developing this in his lab and people around him, one big insight comes from his colleague Karen Spark Jones in 1972, and she basically contributes. She basically makes a simple observation, seemingly simple observation, which is that if you've heard the algorithm TF-IDF, term frequency inverse document frequency, this is basically, she says inverse document frequency could actually carry a signal that term frequency by itself, the frequency of words in a given document, might not by itself contain. And so Karen Spark Jones, like I said, says, what if we actually had how often words appear in all the documents or many documents as a signal of how unimportant they are. Because if it's everywhere, it's probably not as important. But if the unique keywords in a given document are actually signal that that document carries information about that particular word. And so what that does is now you can universally apply the keyword weighting and the vector creation to all vocabulary in general, including the, that, and you and whatever. Because if words are common enough, they'll appear in all the documents and by default automatically get lowered in their weights. So you didn't have to now make sort of careful curation of these are the keywords that we're going to account for, these are the ones that we're not going to. Simply by using regular English language vocabulary, it would automatically work out that common terms like prepositions and pronouns will get lower weighting, and proper nouns will actually show up further. And so one more development on that was the TF-IDF algorithm kind of becomes quite useful for many years, and then a variation of it, BM25, which you may have also heard of in search retrieval engines, basically contain the insights that you also want to normalize for the length of the document, because if a document is longer, then of course the frequencies of words in that document will be more, and as a result it might just somehow always show up as more relevant to the query. And seems obvious, but sometimes it takes a while for people to figure that out as they start using it, and so they start normalizing for the length of documents. And one of the ways they do it is also what they do is if a word appears very often in a given document, maybe only the first few times it appears is what's carrying actually enough signal about it, and after that it's kind of doesn't really add as much information about it. So if I'm hearing the word airplane 5 times and then 20 times after that, it doesn't really mean that additional frequency carries weight. So they sort of account for that. If you look at the BM25 formula online, you can read it. It's very readable. Same thing with TF-IDF, even more readable. There's another approach that people took around that time, 70s I believe, which was LSI. This is a kind of a different approach to using vectors for finding relevance and so on. We're much closer to neural networks actually than this approach, but I'll kind of move past that so that I can move right into vector databases actually, but that I'll do in a bit. So before that though, the advent of the web, I believe, is like a massive mid-step to where we are now. So as the web came around, as we had a lot more information being produced by a lot more authors, almost an inability to be able to properly index manually and even automatically arose, because you just had a lot of spam online, you had a lot of repetitive stuff and so on, and so people started to ask what additional signals could we use. And so a few of the signals that people wanted to use were authority and popularity, especially on the web. And so beyond the information itself, beyond the data that was contained in the documents, people started to especially like Google with PageRank and IBM with hits, started to use the links between documents, or let's say on the web, citations as well as hyperlinks started to be used as additional signals of information, as well as authority, as well as whether something is actually a useful piece of information. So you may have sort of, on a surface level, heard about it before. That's how that worked. And so one of the sort of details of that was that the text that you would put in the hyperlinks to a given website could be used as additional sort of metadata for that website. So it's kind of like content author writes a piece of content, a blog post, puts it out there, then someone else links to that post and says this post is brilliant and talks about XYZ, and now that piece of information from the indexer, from the aggregator, is able to be associated with that piece of actual content. And so it becomes much richer. So not only is it now usable as a way to find relevance to users' queries, but also kind of find whether the content is spam or not spam, or at least helps towards that. So this user-generated metadata thing sort of really kind of starts to change how people view where information about a given document lies, within or without. Very sort of very adjacent to this is knowledge graphs, which were, I believe this is like 2010s onwards, really became sort of popular at Google and so on, which is creating an actual graph database, a complete, like a graph database of documents and their connections to various different types of other documents. So you can imagine a person, entity, organization, entity, an item that exists in the world, a occupation, etc., and just having edges connected to each of them, a proper node graph. And this started to become more popular, especially as they started to visualize people's queries or people's results, the query results at Google, for example, as these boxes on the right or whatever, where you would see like a little bit of a brief about the given thing that people were looking for. So they could say, okay, this thing that you've looked for, if we walk 3 edges in 3 directions, so people that associate with this person, let's say it's an actor, movies that they have been in, as well as what's coming up for them, and they can just, in addition to what they're already showing and outside of the results that exist on the web, which are just web documents, they can explicitly say, we already happen to know that in our graph these 3 people are associated with this person, or are often looked up with this person, and so you see them alongside. So this was how they were doing it, was this knowledge graph traversal. So kind of going back to the vector space model, and people asking, what if we could map ideas into space? We had already approached this problem through the word counts in documents, and we were able to compare them using cosine similarity, and people already were getting useful enough results compared to human labor being put into indexing or retrieval of information that at a scale that was not possible. But once we had, after the advent and proliferation of the web, a lot more data. So a significant amount of data exists on the world now. People have written it, a lot more words just on a basic level that people have written about different subjects, as well as an important other ingredient, which is a large amount of compute, and also concentrated compute in data centers that a single entity could perhaps command. I'm not a fan of the fact that it was private and corporate, but that's just my opinion about it. But the fact that it exists at all, that it could be commanded, a large amount of compute together. Imagine like just everyone's computers at home just being connected to one computer. It just wasn't the case. And so once it was that level of compute was possible in just one building, you can just hit a button and make that choice. People started to say, what if we just process a crazy amount of data altogether, because we just have computers sitting around in a data center, and that allowed them to start thinking about building neural networks for natural language processing. So the first effort around this stuff, or the first significant effort, was Word2Vec, if you've heard of it, which happened at Google, I believe, maybe. And this was a attempt to train a neural network on a large corpus of data from the web, and it would basically create embeddings for words where similar words would end up in a similar point in space. So vectors again, or similar words would have similar, or vectors that would give you a similar cosine similarity. And so another effort like that was GLOVE. So again, the way they're doing it is like, if you have words that occur together in a given piece of text, so you have there was is often seen there first and then was after, while there jump is like not often found. So there being followed by jump, or there just next to jump, is just not associated very closely, while there and was is associated. So this thing is happening at billion scale of just words from the corpus of the internet, and as a result you get a model that at the very least is able to associate similar words. So what you can do on a very ground level, just on a very simple level, is sort of a synonym association thing. So if I look for a query about I don't know, let's say pizza or something. Actually, that's so specific. Let's just say desks. Then it might find table. It might find other pieces of furniture that are associated. It might even find office as a term. It might find whatever else. So whatever else is associated with it. Now, if you go to an e-commerce site and you type in a query that is not quite that, it might be able to not just like correct your typing mistakes, but also find similar linking words or similar co-occurring words, just using this sort of constant time model that it was created, which is GLOVE or Word2Vec. That is like doing it big disservice, because there's much more cooler stuff that you could do with it. But I'll move forward into BERT in 2017. If you heard of BERT, BERT. BERT was, I guess, the first transformer architecture proper, where they had an encoding, they had an encoder, they had a decoder, and the idea was to, I guess in BERT it was only the encoder, but it was the idea of having multiple layers of a neural network that process that information to create the final embedding, which represents that vector. And so I don't have, or at least I'm not going to get into the visualization. If I have created this visualization where you can sort of see vectors walking across the space and sort of get a bit more of a mental model, but I imagine most of you already are familiar with it, but I'll just sort of give you a sense of what they are. Or what the architecture of these models, BERT, sentence BERT, and so on is primarily you have a. Do I care to explain this? Why do I want to explain this? Let me see. On a very fundamental level, you have a piece of text. Let's say a query. You go ahead and process it into a list of words, a list of tokens that you identify in the language. Those tokens are the tokens that this given model understands. Let's say it's BERT, and so there's a vocabulary that you can find, a lookup table for that. You convert that into a list of tokens first based on that vocabulary. Then you based on that lookup table get each embedding for each of those words that were in that table that were trained. And so if I have a sentence like the fox jumps over the dog or something, you get an embedding for the fox jumps over the dog, and then you have this list of embeddings, which is a list of lists of numbers, and you process that matrix through many layers of a neural network, and each layer modifies each of the embeddings. So the embedding starts off a certain way from the lookup table, and through each layer it basically gets updated, modified depending on the tokens around it, and perhaps any instruction you may have given. And by the end of it, each of the embeddings have been updated and look a different way. And so depending on the task, whether you're predicting the next word, or whether you're trying to find a masked word in the middle, masked language modeling, or whether you're just trying to do something else, you can now project back any of the hidden states or an average of all the hidden states back into the vocabulary space, the lookup table that you had at the very beginning from which you gathered the embeddings, and simply say, so the fox jumps, quick, dog are all over here, and I'm going to find the word after lazy dog, the dog, and I'm going to see what neighbor words or what neighbor embeddings or what neighbor vectors happen to be in that space, and I go ahead and grab those tokens, and those become the candidates for the final output. So on a very, maybe not a very clear explanation, but I like having a visual sort of intuition for this. this allows you to see how even large language models work in exactly that way, where you just sort of projecting back this hidden fuzzy state, this vector, back into the vocabulary space simply based on what the closest words are. That's all that's happening in the current models as well. And so this thing is now being applied at industrial scale, and that's the point of it. So yeah, sentence bird, which was like kind of a just bird that does multiple tokens together. Blah blah. Moving to, okay, so I say embeddings and people actually talk about vector embeddings lots, but they actually are not quite as they're not quite as easy to compute and work with as it feels when we're working with small data sets. At scale, when you're working with a lot of embeddings, it actually becomes prohibitively expensive. Because let's say you have 768 dimension embeddings, let's say like bird style, and you have millions of documents or even hundreds of thousands of documents. That's like you multiply all the bytes and so on. You find like it ends up needing a lot of memory to store and a significant amount of data being transferred from one place to another. And so people started to ask, and which means that everything will take forever. So if you're going to make a query and you're going to try and compare the query vector to each of the document vectors 1,000,000 times, it seems pretty inefficient. Let's come up with a way to do it better. So we ask, how do we make search real time at this scale? And so the obvious approach is approximation. I'm very familiar with approximation from like the game industry and so on. We're always trying to like cheat, just like make it look like the thing, but don't actually do all the math. Same thing in films, but also films is different. It's not real time. In games, it's real time. And so all you're trying to do is like just create the door, and then you never look behind the door, and that's fine. That works. And so as long as you can get, or with ray tracing is expensive, and so let's just hack our way to finding a visual that just works. Without having to actually do ray tracing. So in this field of search, we had the approach called approximate nearest neighbor, because like I said, we're trying to find the nearest neighbor, which is why I gave you a bit of an explanation. And that math, if you're doing it against millions of documents, is very expensive to do it in a linear fashion. And so you build an index that is an approximate index or an approach to do it differently. Some approaches within that are HNSW, which is hierarchical navigable small worlds, where you have like these sort of multiple layers of connections, and yeah, it's a whole approach. Look into it, very cool. But it allows that, and other approaches allow you to simply build a less accurate but still very reasonable way to constant time almost query documents using embeddings. And so now it actually can be put into production and has been for a long while. Sort of adjacent to this, I guess like I haven't set it up well enough to kind of get into it, but I really feel like mentioning it. This guy Omar Khattab at Stanford does awesome work. If you heard of DSPy, him and his team have worked on that. But they were exploring this like 2019 and 2020 Cobert, which was approach to be able to do this embedding math a little bit more richly or richer, where instead of having one document embedding, so one embedding for an entire given document, and by the way, you can of course split documents into like having 20 paragraphs in a document and have an embedding for each of those paragraphs. This approach called Cobert was preserving each token's embeddings within that document, and then doing this sort of centroid math. It's very cool. That would allow you to get the benefits of, because one problem, I guess I didn't set it up, which is one problem that people face is that with the semantic sort of comparison, you would get that sort of, okay, this document that I totally would not have expected to be found in relation to this was found, but it doesn't always factor in proper names and entities. So you might not get an exact match showing up in this approach. So most often systems that work well are hybrid systems. So you actually have, and we have various algorithms for them, Splade and a bunch of others, where you're saying weight the results based on this much for the vector approach and this much for the keyword comparison directly. So then that way, if I have Gordon in the query and Gordon in the document, I don't have to just sort of throw my hands up and say, well, semantically that didn't capture it. I can say for sure if you find the keyword, or not for sure, but you weight it and you're able to make up for both words. And most systems right now are in fact using both approaches. The Colbert approach was just kind of cool because it was kind of trying to use the vector embedding structure to get even better lexical comparison performance going on. Lots to talk about in that: dense passage retrieval, reciprocal rank fusion. I just made notes, but not gonna get into it. Can I just get a time check on how much time do you think I have?
30 seconds.
Oh fuck! Really? Yeah. No. Okay, I have time. So no, I have something like that. Probably 10 minutes. Yeah. So now that we had this, we had this ability to, and we had this ability in the last, let's just say, this is 5 years ago or something. We're already working with this assumption, and a lot of systems are using it, e-commerce, general. I mean, actually, not a lot of systems are using it. My view is that just about everything sucks, software-wise. People are not building anything good, just especially anything that's used by, I'll give a quick rant, fuck it. This is insane. We have this green border right here. I don't want this. I put a lot of time into the slides, but this entire office and everyone just accepts the fact that this is supposed to look like this, right? So this is the world that we live in. Point being that even though semantic search exists, people were not using it. But that point aside, assuming that people were using it, we still wanted to go further. And so now that we have this ability to extract documents or for relevant to a given query, could we go further and recreate the human search experience from the Library of Alexandria, where you basically had, you were approaching you would go to a librarian, you would ask a question, or any library actually, why am I going back that far? You ask a question, they fabricate an answer for you based on all the knowledge that they have and all the resources that they can access, and then now you are informed about the topic without having to yourself consume every single document before you can get an answer. I think it's very important still to cite and be able to check your work, but the fact that the librarian or someone who's an expert in general can give you an answer is quite useful. So now that we're able to automatically retrieve documents that are relevant to a query to a given degree of accuracy, people start to explore this idea of RAG, which is Retrieval Augmented Generation. So this is on top of retrieval that we're already doing. Let's use the big affordance that I think that exists of LLMs, which is sort of natural language understanding, natural language manipulation. We can use that as a way to synthesize a natural language answer on top of the results that we just fetched. And so instead of giving the 10 blue links by Google, we instead give you an answer that you can read, 1 paragraph, 2 paragraphs, whatever, ideally done with citations, so that you can go through and check the work that was done. I think there's various UX sort of paradigms that need to be explored, very underexplored space. People sort of just jumped on the citation approach, and no one even clicks on them. So there's lots of issues with the current paradigms. I'm not saying that I have an answer, but I always play with various approaches to building RAG systems. But it certainly does mean that now you can get closer to the answer even faster, perhaps, without having to look through documents. And also, if you are doing that, you are perhaps able to consider a larger amount of documents in fabricating the answer, as opposed to perhaps in Google, if you do see 10 links, you're going to look at 3, and you probably just walk away after that, maybe ill-informed, but with the sense of being informed. In this case, maybe if you are automatically processing a larger amount of information, and you have built a system that is just using enough processes to be able to verify answers, as well as have an approach of distrusting this automatic answer, you just are perhaps a little bit more likely than the 3 links that you see show up as the very first option in a fuzzy system. Within RAG, there's so many cool approaches I would love to talk about, but I'll briefly mention this approach called HYDE, which is hypothetical document embeddings, which is so instead of having the user's query directly being used to find, it's like bait, you're finding which documents are in that pool that are matching this query. You instead say, let me generate a fake answer. Again, language models can do this for you. So just generate an answer without any documents, without any whatever, and then that answer you actually dip that answer into the pool and see which embeddings are closer to that answer. That works actually sometimes better, because if you're asking a question that might not contain the kind of words that might be in the answer, or the question is framed in such a way that where the answer looks just very different. The question might be philosophical and using terminology that doesn't appear, as well as the document might mention names and so on. And so if let's say I ask a question about some kind of topic around science, and the fake answer might contain Feynman or Carl Sagan, then the fact that you're putting the fake document as an embedding containing those names is much more likely to grab other documents with the names of other scientists around it. So very cool technique. There's graph RAG, there's proposition chunking, self-querying, so many approaches that I think are underexplored, because you can go much beyond just like a simple embed the query, grab the neighbors, job done, go home. You should try harder. So anyway, where do we go from here? That's the sort of final closer, which is, I guess currently a state-of-the-art pipeline would include all of them. Not I guess, this is just how it is. The history of information retrieval is, funny enough, one that is like built upon layer by layer, and not one where like dismisses old ideas. And so currently you have a system that would use everything involved. You'd have a document store, you'd have a full text index from 50s style, you'd have knowledge graphs perhaps, you'd have HNSW style vector database to be able to do constant time querying. You would have a re-ranking step, which I didn't mention, as a way to account for precision and recall. You'd have a RAG layer perhaps to synthesize the human language answer along with citations, and that would again produce a system that is a lot more usable. The lesson being that it is not really a solved problem, and it's not really a thing that you can simply walk away from. It is a system that you're trying to make more robust in the service of information retrieval, and that's the task, not let's say a independent researcher or something like that. So yeah, that's it. That's the history of search. Thank you.
Is there any questions? Oh, Sam has a question.
Yeah, I have a question. You kind of outlined the history of information, but I'm curious in terms of where do you think the retrieval methods for information going? And let me give you a perspective. You kind of put together that nice classification closet in Library of Alexandria, right? But it's a deterministic information, and as soon as we put book or publish any report, that information is instantly out of date because we're constantly obtaining new information. And on top of that, the classification categories sometimes is a poor approximation, because if you ask any two humans what is a specific classification category means, they would produce a completely different answer, right? And now with neural nets, what's interesting about neural nets is I'm thinking about the complexity of information, and according to Kolmogorov definition of complexity is what is the information, it defines complexity as the smallest possible program to define a particular thing, which could be a structure, informational structure. But if you think about it in terms of neural networks, the smallest possible program to define a neural network is the neural network is exactly the same size. So if you attempt quantization or anything like that, you're going to suffer information loss. You can't compress a neural network. So it gives us a clue in terms of that a neural network potentially could be the most efficient form of storing information. So then for me, going forward, the question becomes is how much approximation can you tolerate when it comes to the informational retrieval? Meaning okay, well, if it's an image, we can compress an image because that can only process so many pixels per inch, so we can suffer information loss. Same thing with neural networks is how much do we need for specific particular task. So going forward, I'm thinking, well, if we start asking this question, do we need any more informational structures than neural network itself? So I was wondering about your opinion on this.
Thanks for the question. No, really, really cool way to frame it, which is I mean, compression is always like a great way to frame everything. I find I find you can have so many problems that can be framed as compression problems. There's like a paper a few years ago or whatever, like a something to zip or something. Like it was like a you could the compression algorithm of zips, like zip files, was kind of almost adjacent to the compression algorithm of language models. You can look into it. Point is, you asked me a fundamental question, which is like how much approximation you can tolerate and how much that is essential to the problem you're trying to address. I think this is where I always find like very software, like engineer kind of bias, where I use these technologies in a very like, okay, this is a little baby, like it's doing shit, whatever, like I can use it, you know, like I give like talks about like language models, like how they actually work on a lower level. If you are interested in visualizations, you can like find some stuff on my YouTube, which is by the way this one. But you can, once you understand the mechanisms of these models, you're like, this is not that like intelligent. This is just compression, and if you can use that to your advantage of accelerating your query retrieval or accelerating your semantic intent parsing or whatever it may be, then sure, use it. But it is fuzzy, like it is extremely lossy, or it is just lossy in general. And I personally don't tolerate lossy like just algorithms as part of robust applications. You know, like nothing should ever crash. Anything I ever write crashes, it's on me. Let me fix it. And of course it crashes. I'm an engineer. I break stuff as well. But I don't think software should be built on, again, vibe coding, don't get me started, but like software should be built on paradigms that are that lossy and that fuzzy. But if you can use them in some way with guardrails around it, with user experiences affordance around it, where the user understands, I think that's fine. So I would not have like a cool insight about coming up with an algorithm or an approach to explain language models that would be perhaps, because I think it's like a P equals NP kind of problem. Like if you can in fact compress it lower, maybe someone intelligent can actually do that. But I'm again not a scientist. I'm more of an engineer, and so on the applied side, all you can do is be more thoughtful, be more careful as you use these things, and just not put them at the pilot. I put everything into an air gap box. Yeah.
Right?
Yeah.
Because you're for precision, like you're thinking as engineering something,
yeah,
like an engine or.
Yes, it's pretty, yeah, absolutely.
Precise. Okay, but from that perspective, yeah, 100%.
Thank you.
Yeah.
Hi Kushal, thank you for the interesting talk. So I'm a huge fan of just regular full text search, and I think it's like important not to over engineer things, because like with RAG, I mean with vector embeddings, you have to like there's upkeep costs, like you have to host your model. Your vector search is like in the worst case it's linear. I mean it's linear time, so where do you see like using just regular full text search versus vector search, or maybe some other methods? Like how do you pick what's the best for your use case?
Oh shit! Sorry. Yes, there's a microphone right here. I just hit it for myself. I mean, I think that's another thing where I could go on a whole diatribe where, like, I really love tiny models. So I love using, like, again, the smallest appropriate tool for the job, and so that is my way of battling with the problem of, well, this might be unoptimal to use a neural network for this. So what can I do? I am still often using a hybrid approach. So full text search, of course, you need keyword search. But I'm trying to use the benefits of neural network approaches whenever possible. For example, not in this visual, but like this one, I have blah blah blah. Okay, I have like a visualization at the end in this talk where all those embeddings and everything are made by a 300 million parameter model, and so that is totally runnable on your phone. And so certainly in constant time, you could do it in a browser. You could do it, which is like no need to even use your own compute hosted server. But certainly you could do it on a compute, server for 1 million users, even probably at a reasonable enough speed. And so when you, as long as you're like willing to make some concession, which you have to when you're doing approximation and compression, you can pick a solution without completely foregoing. I would say like, I'm happy enough if you have narrowly enough defined your problem, if I have narrowly enough defined a problem where I don't see the benefit of doing a word association or doing any kind of semantic understanding, and keyword will get me that far, then there actually is no point. Like that's just like shoehorning AI into everything. But if you are in fact doing semantic retrieval and a user is at the end of the retrieval, the one asking the question, is you most often want some kind of semantic layer to be able to use it. So I would say yes, and just use the tiniest model possible for the ability to afford hosting that.
So the question is about expertise.
Can't hear you.
The question is about expertise, right? So where does expertise live in this, right? Because once upon a time, humans were making all these indices, right, and classifying all that stuff. And now we're asking machines to do that, and we're discovering that they're not doing it so swell. And we also have this loss of respect for experts, right? So where does that go? Where are we going with that?
It's truly a wonderful question. I think my lean is always towards that, which is like there's a whole movement currently of using language models in an inappropriate way to automate your own sort of tasks and just sort of get away without doing them. And I think that's like a ridiculous thing to think when you come across technology, because what you should be saying is, I have a language model that can actually help me learn this faster or prototype faster, and then I can spend the rest of my day or hour or time learning and actually getting a benefit and after the boost of having seen something working. But so if you do it in the goal of learning, you increase your expertise, and you certainly don't lose in respect for experts, because my whole life is like I'm here because of all the people that taught me all this stuff online. Like I studied film, I didn't study software, but people taught me this stuff anyway because they were willing to share knowledge and they cared all about it. So I have immense respect for people who dwell on subjects and truly think about them. And certainly I don't want to there's a word for it, atrophy my brain by simply just pressing tab all the time and accept that. I hand code everything, honestly. If I show you the code behind this dog, like this is like the scroll radius, the scroll variance. This is like that scroll shelf thing that you saw. Like this whole code base is just for that visual that shows you that bookcase that has the scrolls. So and I hand coded that shit because I just love that shit. I enjoy it. So the point is that you can have a different perspective, but that's your choice. I think culturally, the messaging comes from people that have power to influence, and so messaging about whether AI is dangerous comes from them. Messaging about whether you need experts comes from them, and so I can't fight that battle. I think you can only change your own mind about it.
Okay.
Thank you so much, and thanks for going.